Okay, so continuing on with class 16, here's another example. We have drag on an airplane that's cruising at 240 miles per hour in standard air, and it's determined from tests that on a 1 to 10 scale model in a pressurized wind tunnel, right? So we're going to have a pressurized wind tunnel, and we want to minimize the compressibility effects. We're going to use an airspeed that's the same, right? So it's going to have the velocity, it'll be the identical from the model, the scale model, to the real airplane. Determine the required air pressure in the tunnel, assuming the same air temperature for model and prototype, and the drag on the prototype corresponding to a measured force in the lab of 1 pound. That's on the model. All right. So here is the problem. And do we need? No, I don't need. We don't need to convert the units here. But if we were to take a look at this situation, we would find that the drag, which is the principal thing that we want to try to find in this, was a function of variables including, oh, I don't know, maybe the length of the wing to the length of the airplane, or overall length, whatever. Yeah. So we were saying, like, the or here you go, the width, right? So here's we have the length and we have the width. We also might have the length of the airplane involved, but I will have so I'll just keep them that way. There you go. And we might also have the roughness, right? So there might be some amount of roughness on there. It's just as a typical thing. Oh, I didn't mean to there. I meant to put it into here. There you go. And the density and the viscosity and oh yeah, definitely the velocity. Anything else? Now maybe those are all the parameters, right? So then we find the pi terms for these. In the pi terms, we have a collection, and just as a general thing, noteworthy, they stick a 1/2 in here, and we'll describe why in the next class, why they put the 1/2 in there. L squared are in there, and by the way, by definition, they call that the drag coefficient, right? That's how we define the drag coefficient. And we note that the other pi terms are this length ratio. I'm going to go the width right there. It doesn't matter. It's just the scale. And then also the roughness, and then the density, velocity, and length over viscosity, and we recognize that as Reynolds number. And in order for us to make use of the scale, we have to first make all of these correct. Let's assume that this is that we're going to be able to have the model and the real world, we're going to have the right roughness. And we might actually even, in order to have that achieved, we might actually create some fake roughness. That's actually something that's possible. Sometimes they'll put like little pieces of tape or something like that onto this thing. At least we do on ships. But that's actually for another reason to induce, turbulence, but we'll stop. So first let's get the Reynolds number scale set correctly. And we know that that's going to be this Reynolds number for the model needs to equal the Reynolds number for the real thing. And our big trouble here is we want to figure out what we want to find the pressure here, and we know that the ideal gas law is going to give us a relationship between the density as well. So that's our reasoning for saying let's figure out what that ratio needs to be. And so we were going to have the mu of the model divided by the mu of the real thing, and the velocity of the real thing divided by the velocity of the model, and then the length of the real thing divided by the length of the model. Well, So we could say right here that that's going to be 1 to 1, right? Because we were told that this is 240 and that this is also 240. And we also know that this is going to be a scale of 1 to 10, but the 1 is the model and the 10 is the real thing. So the real thing over the model is 10. What we're going to be left with, therefore, is going to be 10 times the 10 times the ratio of the viscosity. But if the temperature of the model equals the temperature of the real thing, then this goes away. That goes not to 0, it goes to 1. Excuse me. Goes to 1, right? Because the viscosity of the air is dependent really on temperature and pretty much temperature alone. So we're left with this relationship that the ratio of the densities, right, should be equal to 10 in order for this to work out. That's our reasoning by way of rule to be able to get the Reynolds numbers to be equivalent to each other. We can then apply the ideal gas law, and that's going to be what it says, PV equals MRT. Therefore, you would say that R, it's a constant, is going to be P times density divided by temperature, right? Because we have the volume, sorry, other way around, right? We're going to have the volume divided by the mass, which is specific volume, or on the denominator, the temperature, right? So that means the model equal to the real thing, right? So here's the pressure right here. So what we end up saying on here, we know the temperature is going to be equal to each other. So we have the pressure of the model divided by the density of the model equal to the pressure of the real thing divided by the pressure here. So rearranging this, we would say the density of the model divided by the density of the real thing is going to be equal to the pressure of the model divided by the pressure of the real thing, which we know it to be equal to 10. Therefore, the pressure of the model, I'm going to say this right, everything needs to equal to 10 times the pressure of the real thing, and we'll say that that's going to be 14.7. Therefore, the pressure in the model should be at 147 PSIA. PSIA. Wow, brain's not working. I need lunch. PSIA. Right. So that's the pressure. Answering the first part. Determine the required air pressure in the tunnel. We need 147 PSIA. And that's to worry so we don't have to worry about the Mach number being too high. Now, once this is satisfied, with the Reynolds number scale satisfied, right up here, and we'll assume this is satisfied. We'll assume that this proportionality is going to be satisfied. It's a scale model, so it must be equal to 1. We could then say that the drag will be 1/2 rho v squared L squared, and that's of the model, is going to be now the drag 1/2 rho v squared L squared of the real thing. So we could write this out. Our main goal is to find the drag of the real thing. So we'll make a ratio of the model. We'll make a scale ratio here of the velocities, and we'll make a scale here of the proportions, the geometry, and we'll have this equal to the model right there. And note that another way to have written this is lambda density, and that's upside down, right? And then lambda velocity, and that should be, that's also upside down, but it's to the square, so it's the -2. And then this is lambda -2 as well times the drag of the model. So this right here is upside down, right? So that's 1/10, 1/10. This velocity is equal, and then the scale is a 1 to 10, so this is going to be a 10, but it's squared. And then the drag that we get right here is going to be 1 pound. And what this ends up saying is that we're going to expect 10 pounds of drag for this. But keep in mind that we might be limited by a Reynolds number range. But we're probably going to be okay in this one. Chances are. So that is another example, and let's see, I'll start a last example in a new video. So hopefully that'll be useful to you. See you soon.